A very good afternoon, dear students. Welcome to the session CET NEET coaching organized by Udupi Jilla Panchayat and DPUE Udupi. I am taking coordination compounds from the subject chemistry today. I am Mrs. Sushila Holla, lecturer and principal in charge, Government PU College, Koteshwara. By now, I think in your colleges, this lesson is already taught. So I feel you are all aware of the basic definitions, concepts about coordination compounds, which is already taught in your college. Now, before actually stepping into solving the problems, let us just glance through the topics which you have already studied in the classroom. Okay, this is the formula of a coordination compound you are familiar with. Now, when you see this coordination compound, you can see a square bracket here which indicates the coordination entity. Coordination entity, and here this is a central metal atom, and these are called ligands, and ligands donate electron pairs to the central metal atom through coordinate bonds. And the ligands and central metal atoms together make coordination entity or coordination sphere. When they have a spatial arrangement in a definite geometry, it is called coordination polyhedron. And the charge on the coordination entity and this complex ion is neutralized either by positively charged ions or negatively charged ions, depending upon whether the complex ion is positive or negatively charged. And this is the central metal atom. These are called ligands. This is called coordination entity. Now, oxidation number, that is, in this compound, the oxidation number of cobalt is +3. That is balanced by the 3 counter ions. The counter ions are after the coordination sphere, and here these are present in aqueous solution in the ionic form. So these are the ligands inside the coordination sphere lose their identity during bond formation, and they are not free as ions in the solution, but the counter ions either negatively charged or sometimes in anionic complexes in positively charged ions are free in the solutions. Next, this is a coordination polyhedron. You can see the cobalt metal in the center with the octahedral arrangement of the ligands. And these are the counter ions. This is complex ion. These are called simple ions. Next, I told you about ligands donating electron pairs to the central metal atom. So what are ligands? Ligands donate electron pairs. If a ligand donates a single electron pair, it's called unidentate ligand. And among the unidentate ligands, we have neutral ligands, negatively charged ligands, and positively charged ligands, which donate only one electron pair at a time to the central metal atom. Didentate ligands. Ligands like oxalato can donate at a time 2 electron pairs. Even ethylene diamine or ethane 1,2-diamine can donate 2 electron pairs at a time. These 2 nitrogens can donate, and these are called didentate ligands, which form at a time 2 bonds with central metal atom. Now, coming to polydentate ligands, in this structure you can see the nitrogen atoms and as well as 4 oxygen atoms in this compound can donate electrons. So it is called ethylene diamine tetraacetate. So EDTA, it is an important hexadentate ligand. Next.
Ballpoint pen.
Listen. Ballpoint pen. Okay, there are certain other kind of ligands called ambidentate ligand which can donate electron pairs through 2 atoms, 2 ligating atoms we have. For example, in this ligand NO2, nitrogen can donate electron pair or even oxygen can donate electron pair. But at a time only one of them donates, so they are unidentate, but they have two different ligating atoms. Even in this case, sulfur can be the donor or even nitrogen can be the donor in this case. So they are called as ambidentate ligands. Now what is coordination number? In coordination compounds, if you see this one, the platinum is bonded to 6 chlorine atoms which are unidentate. So the number of ligands present around a central metal atom forming coordinate bonds. It's not the number of ligands, it is a number of ligands only in the case of unidentate ligands. Otherwise, the number of coordinate bonds formed, it is the total number of coordinate bonds formed by ligands to the central metal atom. Here it is 6, it is coordination number is 6, here it's 4 unidentate, it is 4. But in this case, because oxalato ion is didentate ligand, at a time one can form 2 bonds and therefore oxalate can form 2 bonds at a time and therefore the coordination number is 6. Same is the case with ethylene diamine which also can form 2 bonds at a time. So oxidation number on the central metal atom, now you can see here copper in this case, cyanide is -4, so there is charge -3, so this should be +1. So oxidation number on the central metal atom is the charge it would carry if you remove all the ligands with the electron pairs, and these oxidation numbers are written after the symbol of the metal in brackets in Roman numerals. Now what is very important is homoleptic and heteroleptic complexes. Homoleptic complexes are the ones which contain a single kind of the same type of ligand. So only ammonia is the ligand, only one kind of ligand is present. And if you have more than one type of ligand, like here ammonia, amine and chlorido, both are the ligands, and in such cases they are called heteroleptic complexes. So homoleptic and heteroleptic complexes. Next, I am not going to discuss in detail about the nomenclature of the compounds, but we know there are some rules to be followed. Always it is a rule that we write the cation at the beginning followed by the anion, and the ligand should be written in the alphabetical order always, and the names of the anionic ligands end in O, like chlorido, hydroxido, etc. But cationic and the neutral ligands are written in the same name type. So, and next, to indicate if there are 2, 3, 4, etc. ligands, then we have to use the terms di, tri, etc. Normally we do that in IUPAC naming. But here if the name of the ligand itself contains terms like ethylene diamine, di it has. So if the name itself contains the terms like di, tri prefixes, then in such cases we normally use bis, tris, tetrakis, etc. to write to indicate the number of the ligands. For example, here it is En2, so ethane 1,2 diamine, it itself has di in its name, and therefore outside to indicate the number 2 we use the term bis. So when we use bis, ethane 1,2 diamine is present in 2 in numbers. And oxidation state of the metal is always written like this in brackets in Roman numbers. If the complex ion is a cation, in cationic complexes having positive charge on the complex ion, then the metal is named as an element like iron, zinc, cobalt, etc. But if the complex ion is anion, the names of the metals end with ate, like zincate, ferrate, or platinate, cobaltate, etc. So that next, these are some of the examples of naming. So here we go for diamine, chlorido, then comes nitrito, but N is the donor, so we write nitrito N, platinum 2. In the same way, here this is the simple ion, potassium, trioxalatochromate, because it is a -3 here, anionic complex trioxalato. Like this, we can name different coordination compounds using the rules followed. Next, we'll move on to isomerism in coordination compounds. You all have studied about isomers last year. So, isomerism is having two compounds having same molecular formula but different properties, physical or chemical, due to different arrangement of atoms, bonds or spatial arrangements, configurations. And therefore, you know very well there are two types, structural isomerism and stereoisomerism. Okay, among these coordination compounds, to discuss about structural isomerism, I am going to discuss about 4 in brief. One is linkage isomerism, the second one is ionization isomerism, and then we have solvate isomerism and coordination isomerism. Okay, what is linkage isomerism? Okay, we'll start with the example. In this compound, it is cobalt, there is pentaamine and NO2 group. And we know that NO2 group is a bidentate ligand which can ligate through nitrogen atom or even through oxygen atom. And in this isomer, the donation is by the nitrogen atom is the donor. And in this compound, oxygen is the donor. Same ligand, but the ligating atoms are different. And even in this case, thiocyanate and isothiocyanate, sulfur is the donor and here nitrogen is the donor. And such isomers which differ only in the ligating atoms of the same ligand are called linkage isomers, and this kind of isomerism is called linkage isomerism. So, linkage isomers are isomers in which the same ligand is bonded to the central atom through different atoms. So, this is about linkage isomerism. Next one, you can see a nitro isomer where nitrogen bonds and oxygen is the donor. They have slightly different colors here, and you can see here this is nitrito N, where N can be the donor or oxygen can be the donor. Cyanide is another example where carbon can donate or nitrogen can donate the electrons. Even isocyanato, either oxygen or nitrogen. Here isothiocyanato and thiocyanato, where sulfur or nitrogen can be the donors. And when ambident ligands are present, such isomerism is called linkage isomerism. Now we will move on to ionization isomerism. I'll just give you an example. Look at this compound. These two compounds have the same molecular formula, amines and sulfate and bromine. Here also bromine and sulfate. What is the difference? I told you when this is in solution, sulfate is inside the coordination entity and will not ionize to give sulfate ions, whereas bromide will be present in the solution as Br minus, bromine will be present. But in this case, bromine is the ligand and sulfate is the counter ion, and sulfate will be free ion in the solution. And here bromine and sulfate can interchange their role as ligand and the counter ion, and such here exchange of ligand and counter ion takes place, and such isomerism in which the ions produced in the solutions are different, that is called as ionization isomerism. So, here bromide is the ion and here sulfate is the ion in the solution. If you add silver nitrate, this will give pale yellow precipitate, this won't, and this will give you a thick white precipitate with barium chloride. In the same way, you can see here the second example, chlorine is acting as the ligand and bromine is the counter ion, whereas in this case, bromine is inside as ligand and chlorine is outside as counter ion. Next is solvate isomerism, like solvent molecules. Normally, let us consider water. Here in this example, you can see water inside. When water is inside the coordination sphere, it is acting as the ligand. When the water is outside, it is simply a solvent molecule, or in sometimes it is water of crystallization. So you can see here chromium with 6 water molecules and Cl3. In the next case, the number of ligand water molecules is 5 here, and 1 water molecule is acting as merely a solvent molecule outside the coordination sphere, but the total number is always the same. So this is known as hydrate isomerism. When water is involved as a solvent, here they differ by whether or not a solvent molecule is directly bonded to the metal ion or present as free solvent molecule in the crystal. So here total number of water molecules remains the same, but inside and outside number will be same, but their role as ligand and the solvent molecules will be different. And such isomers having the same molecular formula, but number of solvent molecules inside and outside acting as ligand and merely solvent molecules differs, that is called as solvate isomerism. This is coordination isomerism, in which you can see both the ions are complex ions. Positive ion is a complex ion, complex anion. Here also complex cation and complex anion. How do you explain the isomerism? In this you can see cobalt is associated with the ligand ammonia and chromium is with the cyanide, but they interchange. Here ammonia, chromium comes to this place, cobalt here, and chromium and cobalt exchange their ligands. When the ligand exchange takes place, such isomerism is called coordination isomerism. This type of isomerism arises from the interchange of ligands between cationic and anionic entities of different metal ions present in the complex. Okay, now let us focus on stereoisomerism. What is stereoisomerism? Stereoisomerism arises when the spatial arrangement of atoms or group of atoms in a compound are different. You are very much acquainted with the geometrical isomers, which you have already studied in the first year. So stereoisomerism is due to different spatial arrangement of atoms or groups in a compound. So there are once again two types. One is called geometric isomerism, the other one is called optical isomerism. You are also well aware of the two types of geometrical isomers, that is cis and trans. Okay, this type of isomerism arises in heteroleptic complexes. If all the ligands are one and the same, you can't expect difference in their arrangement. So some of the ligands should be different, or heteroleptic complexes due to differing possible geometric arrangement should be there. So generally it is found with the coordination number 4 or 6. Okay, we will see the geometrical isomers in square planar complexes MX2L2, where X and L are monodentate ligands. So this can exhibit the geometrical isomerism cis or trans. In this case, you have studied last year also, if identical groups are on the same side, it is called cis form, and if the identical groups are on the opposite sides, it is called trans form. Now you can see this is the cis form of diamine dichlorido platinum complex. This is the cis form and this is the trans form. If a tetrahedral complex is present, it won't give you the geometrical isomerism because the positions relative to each other are one and the same in tetrahedral structure. Next we will see octahedral complexes. In octahedral complexes of the type MX2L4, X is one kind of ligand and 4 ligands are of different type. In such a case, if you take the example of cobalt tetraamine and dichlorido, if you see at the beginning, if chlorine two identical ligands are on the opposite side, it is called trans, and on the adjacent sides, chlorine 2 here or here, anywhere when the two chlorine atoms are adjacently placed, it is called cis form, and when they are opposite to each other, it is called trans form. Another, these geometrical isomers are possible even with the didentate ligands. Didentate ligands. You can see here, this is a unidentate ligand and this is a didentate ligand having two ligating atoms. For example, if you go through dichlorido bis ethane 1,2-diamine cobalt complex, here 2 chlorine atoms and 2 ethylene diamine. So once again, if you have 2 identical groups like chlorine on the opposite side, it is called transform, and if they are adjacent to each other, it is called as transform. I'm sorry, this is called cis form. Okay. Octahedral complexes of type M, A3 and B3. So 3 ligands of one type and 3 ligands of another type. We have 2 types of isomers possible here. One is facial isomer, other one meridional isomer. How do you identify them? Facial isomer, if you see an octahedral, there is a triangle in one face, and if identical groups fall on the corners of octahedral face, it is called the 3 corners of a face of an octahedron, that is called as facial isomer. And if the positions of the donor atoms are around the meridian of the octahedron, that is called as meridional isomer. You can see here, this makes one face of octahedral which is occupied by identical atoms. Identical atoms occupy the 3 corners of a face of the octahedron, so it is facial isomer. And here you can see this passes through the metal atom, meridian, and if you have 3 atoms passing through the meridian, identical atoms, then it is called meridional isomer. Next, optical isomerism. You have studied in haloalkanes this year about optical isomerism. One isomer will be dextrorotatory and the other one will be levorotatory. And this is also possible only when the mirror images are non-superimposable and they are called enantiomers. And here the molecules ions that cannot be superimposed are called chiral. All these things you have already studied. One is called dextrorotatory, the other is called levorotatory. So optical isomerism is common in octahedral complexes having didentate ligands. Didentate ligands. You can see here there are 3 didentate ligand molecules here, ethane 1,2-diamine. Here you have to remember only cis isomer shows the optical activity and not the trans isomer. Why the trans isomer is not optically? Because it is symmetric in nature. If you have a ligand like this, it has plane of symmetry and the mirror image will be superimposable, and therefore only cis isomer in this case will have optical isomerism. Example is dichlorido bis ethane 1,2-diamine platinum complex has cis, this is cis form, both are cis forms, and this is the mirror image, and these two are non-superimposable mirror images and they are optically active isomers. So they are isomers, optical isomers. Even in this case, COEN3, all the 3 are ethane 1,2-diamine. Here also when the mirror images are non-superimposable, and that is why they are called optical isomers. Next is Werner's theory, which is very, very important to you, not only for this, even for the annual examination, it's very important. There are 4 postulates given by Werner in his theory, where he says the metal atom or ion has 2 types of valencies. One is called primary, the second is called secondary. Primary valencies are ionizable, and it is normally the oxidation state of the metal, and they are satisfied by negative ions. And the secondary valencies are non-ionizable and are satisfied either by neutral molecules or by ions. And the secondary valency is nothing but the coordination number and is fixed for a metal. And the last one says the secondary valencies arrange themselves around the central metal atom in a particular geometry, which gives a particular spatial arrangement and geometry to the compound. Next comes valence bond theory, where we get the idea about hybridization. The different atomic orbitals present in the valence shell of the metal atom undergo hybridization using their orbitals and give a set of new orbitals, hybrid orbitals, which then are allowed to overlap with the ligand orbitals. So, the hybrid orbitals present in the central metal atom overlap with the ligand orbitals forming coordinate bonds. So, then based on their magnetic behavior, it is possible to predict the geometry of the complex ion also. Okay, now if the hybridization, we have studied this in chemical bonding last year also, if it is sp, the structure expected is linear, sp3 tetrahedral, dsp2 it is square planar, d2sp3 or sp3d2, the structure will be octahedral. So, this is octahedral, tetrahedral, square planar, trigonal, bipyramidal, square pyramidal are the different types of. Okay, now you have 4 very important structures you have to study based on VBT, that is about their hybridization, their structure and their magnetic property. Just in brief to tell you about cobalt hexamine compound, hexamine cobalt 3 plus ion. Here the electronic configuration is 27 atomic number. So, electronic configuration is 3d7 and 4s2. When it is cobalt 3 plus the 2 electrons and this becomes 6 and therefore 3d6. Now, if you look at this ligand, it is called a strong ligand. The strong ligands forcibly pair the electrons and these electrons get paired up making 2 d orbitals available for hybridization. So, 2d and 4s and 3p undergo hybridization to give d2sp3 6 hybrid orbitals, to which the 6 ammonia molecules donate their electron pairs. So, due to the 6 electron pairs, the compound gets the structure, geometry is octahedral, hybridization is d2sp3, and because of the absence of, because of pairing there are no unpaired electrons, the magnetic property is diamagnetic. In this compound, you can see fluorine is a weak ligand and with the same configuration of 3d6, there is no electron pairing and therefore the orbitals used are from the outermost shell and therefore this is called outer orbital complex. The previous one is called inner orbital complex. Because of the presence of unpaired electrons as they are, without pairing it's called high spin complex or spin free complex. Now the outer d orbital is used and that's why it's called as sp3, actually it should be 2, sp3 d2, it should be sp3 d2 hybridization. As usual, once again the geometry is octahedral and because of the presence of unpaired electrons, it is paramagnetic. In the same way, if we study about nickel tetracyanide, nickel is 3d8 4s2 and nickel 2 plus 4s2 is gone, 3d8, you have 2 unpaired electrons, but cyanide is a strong ligand, forcibly electron pairing takes place, leaving 1 orbital vacant. So, D, yes, we need 4 hybrid orbitals, D, yes, and 2 hybrid orbitals. So, dsp2 is the hybridization where 4 lone pair of electrons from cyanide will occupy these and you can see there are no unpaired electrons, so it is diamagnetic, and inner orbital complex because of pairing 1 d orbital gets vacated. And the structure dsp2, the geometry is square planar and it is diamagnetic because there are no unpaired electrons. And when the cyanide is replaced by chlorido, which is a weak ligand, here in the same case you can see there is no electron pairing taking place. So, 1, 2, 3, 4. So, sp3 will be the hybridization. 4 hybrid orbitals will get electrons from 4 chlorine atoms. So, because of the presence of unpaired electrons, it is a paramagnetic substance. So the geometry is sp, because of sp3 hybridization, the geometry is tetrahedral and it is paramagnetic. Next, moving on to a very important concept called crystal field theory. Here it is an electrostatic model which considers metal ligand bond to be purely ionic, which arises due to electrostatic interaction between the metal ion and the ligand. Ligands are now treated as point charges. If they are anions, it's okay, or dipoles in the case of neutral molecules. Here what is very important is when the ligands are approaching the d orbitals of the metal atom, earlier the 5 d orbitals have same energy, but when from the far the ligands are approaching the metal atom, their energy gets raised, and then due to the direct intervention of the electrons of the ligands to certain d orbitals which come in the same direction as the approach of the ligands, those orbitals which are directly in the same direction of approach of the ligands will enhance, the energy will be raised and their degeneracy is lost. So the 5d orbitals which have similar energy will now split into two sets which have difference in their energy, and this is called splitting of the d orbitals. That is called crystal field splitting. We call it as crystal field splitting. You can see in an octahedral coordination entity, if you see 6 ligands when approaching the metal atom, the electron repulsion between the electrons of the metal d orbitals and the electrons of the ligands takes place. And when the ligands are approaching in octahedral manner, these two orbitals come directly in the same direction. Their lobes are along the axis where the ligands approach, and they will experience more repulsion and will be raised in their energy. Whereas the 3 orbitals whose lobes are in between the axes are lowered in the energy relative to the mean energy. So this degeneracy of the d orbitals has been removed due to the repulsions of 2 electrons, and therefore they split into 2 sets. 3 orbitals of lower energy called T2G set and 2 orbitals of higher energy called EG set. So this splitting of the degenerate levels is called crystal field splitting, and the energy difference between the two is called crystal field splitting energy delta O representing octahedral geometry. Thus the energy of the 2 EG orbitals will increase by 3/5 delta O, and that of 3 T2G will decrease by, this will be evident from the next picture. This is the direction of approach of the ligands. So this is a very clear picture of crystal field splitting in octahedral field. This is the energy increasing, and metal d orbitals in the isolated metal ion have similar energy. Average energy increases when the metals approach from the spherical field from far, but when the ligands approach very near, there is splitting in the according to the direction of approach, and in the octahedral you can see this is called T2G set, which contains dxy, dxz and dyz, where they get lowered in their energy relative to the mean one barycenter, and this is dx square minus y square and dz square. So dz square and dx square minus y square. And from the mean energy, the energy of the EG set will be raised by 3/5 delta O, and lowering of energy for the T2G set is 2/5 delta O. So this is minus 2/5 delta O, this is plus 3/5 delta O, and this is the nature of crystal field splitting in octahedral field. So depending on the strength of the ligands which can produce the splitting, some ligands can produce only small amount of splitting and some can produce larger amount of splitting. The ligands are arranged in the increasing order of the produced splitting of crystal field, and that is called spectrochemical series. And here you can see the carbon monoxide is at the top, which produces larger splitting, and comes cyanide. And you can see the carbon donors. If the donor atom is carbon, that comes first, and then comes nitrogen, then comes oxygen, then come halogens. So carbon donors, carbon, cyanide, etc. have very high splitting tendency, and followed by donors here. In this also nitrogen, here also nitrogen, and then donors like oxygen, and then come halogens. Halogens are at the end of the series, which produce a small amount of splitting. So here the splitting is very less, and here the splitting is very high. So the ones which produce large amount of splitting are called strong ligands. So these are called strong ligands, and the ones which produce small amount of splitting are called weak ligands. Okay, for D4 ions, okay, if you have in this case, if there are 3 electrons entering the d orbitals, it's fine, no problem. With the entry of the 4th electron, we have to see whether the electron will go to this level or this level. That depends on 2 factors. One is the amount of splitting, that is delta O, crystal phase splitting energy. The other one is called pairing energy, the energy required for pairing of the electrons. And in this case, if delta O is smaller than pairing energy, the electron will prefer, if delta O is small than the pairing energy, electron will go, the 4th electron will enter the upper level, and the configuration will be 2G3 and EG1. Ligands which produce small splitting are weak field ligands or high spin complexes, because they enter into the upper level leaving the electrons unpaired, so high spin complexes. If otherwise, what happens is, if the splitting energy is more, in case of strong ligands, if the splitting is more and pairing energy is less, the electron will not go to the upper level. The 4th electron will prefer getting paired here, and therefore that is the case with the strong field ligands, where forcibly pairing takes place. I told you while explaining the structures. If the strong ligands are present, electron pairing takes place, and low spin complexes are formed, inner orbital complexes are formed. And if the splitting is less in the case of weak field ligands, no electron pairing, they will go to the upper level with more number of unpaired electrons, and they become diamagnetic. And this is how we can explain. If it is very large, it gets paired here, and diamagnetic and low spin complexes in the case of strong ligands. And in the case of weak ligands like water, where the splitting is very less, energy is less, and the electrons will prefer to go to the upper level because the pairing energy is more. In such cases, more number of unpaired electrons will be present, so it will be paramagnetic and high spin complex. Crystal field splitting also takes place in tetrahedral complexes, coordination entities, where the pattern is completely inversed when compared to the octahedral manner. If you have same metal, same ligand with same metal ligand distances, if you compare the two splittings, the tetrahedral crystal field splitting will be only 4/9 of delta O. So delta O splitting will be more, and the delta T will be lesser than half of the octahedral splitting. Consequently, the orbital splitting energies are not sufficient, because splitting is very less in the case of tetrahedral. We normally find high spin complexes, not low spin complexes. So this is the inverted structure. You can see the EG set comes with the lower energy, and the T2G set will be raised in the energy. Color in coordination compounds, you have studied, it is due to these unpaired electrons present in the lower D set, T2G set, which absorb energy from the visible radiation of a particular length, because delta is equal to energy, that is equal to h nu. A particular frequency radiation corresponding to this energy is absorbed, and the mixture of remaining colors will be complementary color that is given to the solution. So bonding in metal carbonyls, I won't discuss much about bonding in metal carbonyls. But there is one thing you have to remember, in bonding in metal carbonyls become stable and the bond becomes very strengthened. That is due to synergic effect we call. What is this? You can see the ligand carbon donates a lone pair of electron to the hybrid orbitals of the metal, that is metal carbon sigma bond. Donation of electron pair from the carbon to the metal atom, whereas there is back bonding taking place where the electrons of the metal atom will overlap with the anti-bonding orbitals of carbon monoxide. So that is MC pi bond is formed by the donation of pair of electrons from a filled d orbital of the metal to vacant pi star orbital of carbon monoxide. So because of the presence of two bonds, the bond becomes stable. So applications, I am not going to discuss much about the applications. In the extraction processes we use, purification of metals and electroplating, etc. we use this. Okay, with this synopsis, let us get into solving some of the questions which have normally appeared in the previous years, CET and NEET. Okay, now we will see the first question. 1 mole of a complex compound CrH2OCl3 gives 3 moles of ions in solution, 3 moles of ions in solution, and 1 mole of the complex reacts with silver nitrate to give 2 moles of AgCl. You know very well, nitrate will react with Cl to give AgCl precipitate. So 1 mole of silver will give 1 mole of AgCl. Now 2 moles of AgCl are formed, means we should have 2 moles of AgCl as free ions. So 2Cl minus should be present as free ions. Identify the answers where chloride is present as a free ion. That means not inside the coordination entity, it should be outside the coordination entity. Now if you see, these two can't be the answers because chlorine is acting as a ligand here, but in this case you can see chlorine outside, and this case also you can see 2 chlorine outside the sphere. Here it is only 1, but we are getting 2 moles of silver chloride, and therefore the answer is the D with 2 chlorine ions, chloride ions as counter ions which are present as free ions in the solution. Okay, next one we will see the IUPAC name example. Okay, this is, there are 3 molecules of ethane 1,2-diamine with cobalt and sulfate. What is the correct answer? Here IUPAC name ene is called ethane 1,2-diamine, and therefore this can't be the answer, this can't be the answer. Ethane 1,2-diamine, this is ethylene diamine. So very obviously you can tick C because it is tris, ethane 1,2-diamine, cobalt. There are 3 sulfate 3, and to balance the charges you have, this is 3 plus, and you have 3 into 2 6, 3 into 2 6. So it is cobalt 3 sulfate, and the answer is C, tris ethane 1,2-diamine cobalt 3 sulfate is the correct answer. Next one is the coordination number of iron and cobalt in the 2 complexes. In this case, the coordination number of ion, the oxalato ion is a didentate ligand. Didentate means it forms 2 bonds at a time, and therefore 3 is not the answer. The coordination number is 6 here because of it is a didentate ligand, and here it is a monodentate ligand, so it is 4, and the option can be 6 and 4, C is the answer. So it is a didentate ligand, so answer is C, 6 and 4. If you go to the fourth one, considering water as a weak ligand, the number of unpaired electrons in this complex, water as a weak ligand. So in this complex we have to see manganese is 25, it is 4s2 3d5. So if water is a weak ligand, the 5 electrons do not get paired because water is a weak ligand. In the presence of weak ligand, there is no electron pairing taking place. Therefore, number of unpaired electrons remains 5. So the answer is Mn25. So the oxidation state is +2. Electronic configuration is 3d5. So water being a weak ligand, no electron pairing takes place, and therefore the answer is 5. Going to the next question, among the following ions, which one has the highest paramagnetism? Paramagnetism is related to number of unpaired electrons. Number of unpaired electrons. So in these metal atoms, in the ionic state, we will calculate the number of atoms first. Chromium is 3 plus, chromium is 24, it is 3d5 4s1. So Cr2 plus, if you consider, it will Cr, it is 3 plus here, 3 plus, it will be 3d3, so N will be equal to 3. In the case B, if you consider iron, it is 2 plus state, iron is 26, so it is 3d 6 4s2, Fe2 plus will be 3d6. 3d6 means number of unpaired electrons will be 10 minus 6, it will be 4. In the case copper 2 plus, copper is 29, it is 3d10 and 4s1. It will be copper 2 plus will be 3d9. So 10 minus 9, N will be equal to 1. And in the last case, if you consider zinc, zinc atomic number is 30. So it is 3d10 4s2, Zn2 plus, therefore Zn2 plus is 3d10, number of unpaired electrons is 0. And if you compare this one 3, 4, 1 and 0, you can see in the second example, highest number of unpaired electrons leading to highest paramagnetism. So the answer is B. So highest number of electrons N equal to 4 is ferrous. Therefore, the answer is B in the choice. Next one, the central atom in a coordination compound is Lewis acid, Lewis base, Bronsted acid and Bronsted base. Last year in chemical equilibrium, you have studied the concept of Lewis acids and bases. The one which accepts an electron pair is termed Lewis acid. So it is Lewis acid. Now in the coordinate compounds, you see metal accepts electron pairs from the ligands. So metal atoms or ions are electron acceptors and therefore they are called Lewis acids. So metal atoms or ions are Lewis acids as they accept electron pairs. So answer is Lewis acid. Okay, next question is, these two show the different types of isomerisms are written here. So in this case, if you see, look at the structures. It is Cl3 same, everything is same, but if you concentrate on this, you can see here it is NO2 and here it is ONO, and you have studied as ambidentate ligands. Ambidentate ligands can donate, this can donate either through nitrogen atom or through oxygen atom. So when the isomerism is due to different ligating atoms of the same ligand, it is called as linkage isomerism. So the answer is linkage isomerism, where you can see the two which are here, N is the donor, this is nitrito N, and here O is the donor, nitrito O. So this is, okay. In this case, square planar complex MABXL shows following set of isomers. How many isomers does this show? First we will see, there are many options here. We will try to write the structure. It is M, A, B, X, L are 4 unidentate ligands. So let me fix the position of A here and B here, X and L. Now, when the 4 ligands are different, let me fix these 2 ligands positions. Okay, if they are on the same side, let me take this as cis. Let me take this as cis. Next, I will fix A and change the positions as L will come here, B will come here, and X will come here. I rotate like this. So here A and B are opposite to each other. If I take this as trans, I will take this as trans. Again, I will change the positions in the third isomer as A, L will come here, and X will go here, and B will come here. And in this you can see once again A and B on the same side, and therefore this is the case, once again it is cis. You can do this rotation with any of the 2 ligands, you will get 2 cis forms and 1 trans form. So in the 2 cases you will have the identical groups on the same side like this, AB and AB on one side, and in one structure you will get the 2 ligands opposite to each other, and altogether I have the answer as A, 2 cis and 1 trans isomer. Okay, next question is, for the CFSE, crystal field splitting energy in octahedral complexes, there are 4 choices. This is crystal field splitting in octahedral complexes. We know the splitting is like this in octahedral complexes. You have EG set here and you have T2G set here, and this is the mean, and here it is 2 by 5 delta O. The energy increases by 2 by 5. Here the energy increases by 5. Now the options are, we'll see the first one, energy of the EG orbitals will decrease. The first itself is wrong because energy of the EG orbital is increasing here. Energy of the EG orbitals will increase, this can be the answer. The energy of the EG orbitals will increase, this can be the answer, and not this. Among these 2 we will see energy of the EG orbitals will increase by 3 by 5 delta O, and that of the T2G will decrease by 2 by 5, and that should be the correct answer, because the next one is the energy of the T2G will increase by 2,5. So this can't be the answer. So the correct answer is the energy of the EG orbitals will increase by 3 by 5 delta O, and that of T2G will decrease by 2 by 5 delta O, and therefore the correct answer can be only B and not the other one. So this is the crystal field splitting which you have already studied, and here you can see the energy difference is 2 by 5 and here it is 3 by 5. Okay, we will go to the next question. Homoleptic complexes among the following are. Among the following, the homoleptic complexes, if you see, what are homoleptic complexes? Homoleptic complexes are the ones which contain a single type of ligand. Here you see oxalato is the ligand. Here there are 2 different types of ligands, and the third one once again contains same type of ligands, and therefore both are homoleptic complexes. So the answer 1 only is wrong, 1 and 2 are wrong, 1 and 3 is the correct answer. So, the correct answer is answer C. 1 and 3 both contain one type of ligand. So, C is the correct answer. Okay, next one is the complex ion having minimum CFSE. Minimum CFSE means crystal field splitting should be very less crystal field splitting. And we have seen about strong ligands and weak ligands. Weak ligands produce small amount of splitting, whereas the strong ligands produce high amount of splitting. And therefore, with the minimum CFSE means the splitting amount should be very small. And we have also seen spectrochemical series where CO produces the highest effect, followed by cyanide, and then we have ammonia, nitro. So, carbon donors have high splitting, and then come nitrogen. Here nitrogen is the donor, and then come oxygen or water where oxygen is the donor. Lastly, we have chlorine. Here the amount of splitting produced by chlorine will be very less, which is a weak ligand, and therefore the answer can be only D, which produces minimum CFSE. So, according to this, carbon monoxide produces the large, here more splitting, and if you come in this direction, the last is chlorine, and therefore D is the correct answer. Okay, here the correct order of wavelength of light absorbed in the complex ions. I told you the electrons present in the lower T2G set will absorb energy from the visible radiation, and they jump to the higher D set, that is EG set. So, during this, the wave, if you go to the crystal field splitting, if this is delta O or E, it is equal to H nu, that is equal to Hc by lambda. So, more the splitting, more the energy of the splitting, lesser will be the wavelength. So, the strong ligands which produce more splitting will have shorter wavelengths. So, the strength of the ligand and the splitting wavelengths are inversely proportional. And if you see here the type of ligands, the first one has ammonia along with, even though ammonia is a strong ligand, along with this there is chlorine which is a weak ligand. So, the splitting is slightly reduced in this case. Here it is ammonia, here is cyanide. So, according to spectrochemical series, cyanide produces the highest splitting and the shortest wavelength, and you have to go for the selection where this has the highest, this is the number 1 highest wavelength, and this is the second one, and this is the third one, and the answer is A, where the shortest wavelength, highest energy and shortest wavelength is for cyanide complex, and then comes ammonia, and the effect of ammonia is reduced by the presence of chlorine in the first one. So, the correct order, the answer is this one. Okay, next, the CFSE for octahedral cobalt complex is 18,000 centimeter inverse, and the CFSE for tetrahedral complex, here you can see metal is the same, metal ion is the same, ligands are same, and in such cases I have already told you delta T is equal to 4 by 9 delta O in the case of same metals and same ligands. And if 4 by 9 into delta O, crystal field splitting in octahedral is 18,000, and it will be 2,000, the answer will be 8,000. So, the choice will be C, that is 8,000 centimeter inverse is the CFSE for the tetrahedral complex using the same metal and the same ligand. So, it is 4 by 9 delta O. So, the answer is C. Next, the FeCO5 the FeCO bond possesses. It's a metal carbonyl. I have already told you in this compound there is donation of electron pair from the carbon to the central metal atom through sigma bond, and there is a d orbital electron from this will go to the pi star antibonding orbital present in carbon monoxide, and this is called back bonding. And this in metal carbonyls there are two types of bonds. One is sigma bond, the other one is pi bond, and the answer is quite obviously it will be, there are two types of bonds, one is sigma and one is pi bond. So you have already seen this. This is sigma bond and this is back bonding by the d orbitals to the vacant pi star antibonding orbital of carbon monoxide, and therefore the answer is both sigma and pi characters. Okay, next one we will see among CONH3,5BrSO4 and the second one CONH3,5SO4Br. The one which gives white precipitate with barium chloride. You have done in the laboratory for sulfate radical. When sulfate radical is added with barium chloride, we get white thick precipitate of barium sulfate. So you have to search for that compound which gives free sulfate ions in the solution. Here there is sulfate ion outside the coordination sphere, so it is present as sulfate ion in the solution, but in this compound sulfate is present inside the coordination entity and therefore it is not present as free ion in the solution. Therefore only this can give you white precipitate with the barium chloride solution, and therefore the answer will be A only can give you precipitate of barium sulfate. The next question is the one which is not an ambidentate ligand. Not an ambidentate ligand, which means it has a single donor atom, not two ligating atoms. Now if you go through this ion NO2 minus, nitrogen can be the donor as well as oxygen, and therefore this is a bidentate ligand. Here sulfur can be the donor and nitrogen also can donate its lone pair of electrons to the metal ion. Here both carbon and nitrogen can be the donor atoms, and if you go to this, only nitrogen can donate electrons and not hydrogen, and obviously the answer which is not an ambidentate ligand, the answer is D. Okay, going to the next question. If in this case hexafluorocobaltate is found to be a high spin complex. It is a high spin complex. The hybridization of cobalt is, cobalt is 27, it is 4s2 3d7. In the 3 state it will be 3d6. So if you find here 6, it is found to be high spin complex because fluorine is a weak ligand. It cannot forcibly pair the electrons. So when the electron pairing does not take place, the hybridization which needs 6 hybrid orbitals obviously will take 4s, 4p and 4d. So sp3 and 2 orbitals of d, and therefore hybridization will be sp3d2. It is an outer orbital complex because fluorine being a weak ligand cannot force electron pairing in the inner d orbitals, and therefore outer d orbitals are taken for hybridization, and therefore it is not the inner one. It can't be this because 6, it is sp, this can't be this. So only A and D are possible, but in this case you can see The answer is D, sp3, D2. Okay. The complex hexamine platinum 4 chloride will give dash number of ions on ionization. So first we will write the structure platinum hexamine. So hexamine chloride. So the problem is how many chlorides to write. So when you are given the name, to write the formula, you have to be careful in balancing the positive and negative charges. In this case, platinum has +4 oxidation state. The oxidation state on platinum is +4. This is neutral, so this will be +4. So to balance 4 positive charges, you will need 4 chloride atoms and ions, and therefore it should be Cl4. So if this is the structure, so you will have -4. If this is dissolved in water, you will get one complex ion of this type. This is one complex ion, and you will have 4 Cl- ions in the solution. So altogether 1 + 4, you will have 5 ions in the solution, and here C is the answer. So platinum hexamine, this is the actual structure which will dissociate to give one this ion and this one. Totally 5 ions will be produced. Next question, we will concentrate on this question. The expected spin only magnetic moments for Fe hexacyanido and hexafluorido are. So you have to go through the electronic configuration. This is 26, so it is 4s2 3d6, and the number here it is -6, this is -4, this is +2, and here it is -6, it is -3, so it is +3. In this case, first compound it's +2, it is 3d6. So 3d6 okay. Now we will concentrate on the nature of the ligand. Cyanide ions are strong ligands, forcibly electron pairing takes place, and therefore 2 orbitals will be vacant available for hybridization, and therefore number of unpaired electrons will be equal to 0, and therefore magnetic moment will also be equal to 0. And this structure, if you go through, it is Fe3 plus state, so it will be 4s0 and 3d5. So there are 5, this is Fe3 plus and this is Fe2 plus. In this compound, second compound has +3. So 5 unpaired electrons. Now look at the nature of the ligand. This ligand is a weak ligand, cannot forcibly pair electrons, and therefore it uses the outer 4d orbitals for hybridization, and therefore you have all the electrons in the unpaired state itself. It's a high spin complex, and the number of unpaired electrons is 5. And if you go to this one, you can see the magnetic moment will be 0 in this case, and here it is square root of 5 into 5 plus 2, so it will be nearly 5.9. So the answer should be obviously D, 0 and 5.92. Okay. The next question is the primary and secondary valency of platinum in this compound. So primary valency is nothing but the charge or oxidation state of the metal ion, and the secondary valency is its coordination number. So in this compound, this is neutral and 2 chlorine atoms are there with -2 charge, and therefore platinum should be +2. And what is the coordination number? Coordination number is the total number of coordinate bonds formed around the central metal atom. Now 2 chlorines plus 2 ethane 1,2-diamine form 4 bonds because it is a didentate ligand. So plus 4, the coordination number is 6 and it is plus 2. 2 and 6. So obviously D should be the answer. The valency is plus 2, that is primary valency is plus 2 or oxidation number or charge on the metal ion, and the coordination number is 6 because 2 from chlorine and 4 from ethane 1,2-diamine. Okay, the next question which has come in the previous year CET is the hybridization of central metal ion in this cyanide complex and this is chloro complex. So in nickel tetracyanide, nickel is 28, so 4s2 3d8. In this case, nickel has valency, so 2, it is plus 2 here, and in this case also 2 minus, so this should be plus 2. So in the plus 2 state, it is 3d8. Okay, this is 3d8. So cyanide, this is 3s, 3d, 4s and 4p. Now if you look at this, I need 4 hybrid orbitals to be formed available vacant for the donation of 4 electron pairs in this case also and this case also. And here to make 4 orbitals available, you can see in this case nature of the ligand. Cyanide is a strong ligand, forcibly electron pairing takes place and 1 orbital will be kept free. So yes, this d orbital 1, 2, 3 and 4. So this will be hybridization dsp2. So the hybridization of the first one will be dsp2. So these two can't be the answers. We will see among these two. So dsp2. Next, if you take nickel tetrachlorido complex 2 minus, here once again in the same way you have 8 electrons in the 3d orbitals and then 4s and 4p. Okay. So in this case, if you go through chlorine, which is a weak ligand, if you go through chlorine, which is a weak ligand, cannot force electron pairing, and therefore these 2 orbitals are not available for hybridization, but I need 4 hybrid orbitals. So the hybridization will be S and P3, this will be sp3, and therefore the first hybridization is dsp2 and this can't be the answer now. So the first answer is correct. So the answer is A, dsp2 and sp3. So due to the effect of strong ligand, electron pairing takes place. So the hybridization is dsp2, and in the second case no electron pairing and therefore the hybridization is sp3. Okay. The metals present in the coordination compounds chlorophyll, hemoglobin and vitamin B12. All these 3 which are very much in acquaintance in our daily life are coordination compounds. So in chlorophyll has magnesium metal in it. Hemoglobin of course is a complex of iron, and vitamin B12 contain cobalamin. We say it's cobalamin which contains cobalt as the metal. So the correct order is magnesium, iron and cobalt. So these 2 can't be the answers. Magnesium iron and cobalt. So the correct answer will be B, magnesium, iron and cobalt will be the correct answer. Okay. Next question we will see. The magnitude of CFSE, crystal field splitting energy delta O, can be related to the configuration of d orbitals in a coordination entity as. Okay, there are 4 options. In the first, we have 2 energies to consider. Here one is crystal field splitting energy, the other one is pairing energy. So we'll consider the first one. If the splitting is lesser than the pairing energy, if the splitting energy delta O is lesser than the pairing energy, if the splitting energy is less, the 4th electron will try to go to Eg level, and therefore the configuration will be T2G3 and Eg1. So T2G3 Eg1, and if the splitting is less, it is due to a weak field ligand. So the ligand is weak field. When the number of unpaired electrons increases due to the movement of electrons to the upper Eg side, therefore it is a high spin complex. So this looks to be the correct answer. This is the correct answer. But let us see, if delta O is more than P, it is not a weak field ligand. If the splitting is more, it is a strong field ligand. This can't be the answer. If splitting is more, it is a strong field ligand. But when the strong field ligand it is more, splitting is more, electron pairing takes place, and it should be a low spin complex, and this can't be the answer, and this is not possible. So the A is the correct answer. So you have 2 choices. If splitting is less, the 4th electron enters one of the Eg orbitals, giving the configuration T3Eg1, and ligands for which this happens are called as weak field ligands and form high spin complexes, and therefore A is the correct answer. Okay. The spin only magnetic moment of tetrachlorido nickel 2 ion, spin only magnetic moment. For that we need number of unpaired electrons. It is 28. Here it is -4, it is -2, should be +2. In the +2 state, nickel has 4s0 and 3d8. Here you can see 4s0 and 3d8. So the number of unpaired electrons here, chlorine being a weak ligand, cannot force electron pairing, and therefore 2 electrons will be in the single state, unpaired state. Therefore number of unpaired electrons will be 2. When the number of unpaired electrons is 2, if you apply the formula mu is equal to square root of n into n plus 2, this comes to around 2.9, or you can say 2.84. So B should be the answer. Okay, so the next one is tetramine aqua chlorido cobalt 3 chloride can be written as. Now you are given the name, you have to write the correct formula for this. Tetramine aqua chlorido cobalt 3 chloride. Tetramine is okay. Chlorido is okay. Cobalt 3 chloride. Now how many chlorides do you write outside? So here it is tetraamine. So 4 amine groups, chlorido 1 chlorine group, cobalt is 3 plus. Cobalt is 3 plus. If cobalt is 3 plus, you have -1, and therefore +2 will be the charge on this cation, +2. To balance this +2, you will have to have -2 here. Therefore I need 2 chlorine atoms, and therefore this is the expected structure. You have Cl2. Cl2 is present in this compound, so the answer should be B, CO, CO. There is aqua, I'm sorry, there is one aqua here. So water should be present here. So the correct formula will be CO, Cl, water and ammonia, tetraamine and aqua chlorido. So this will be the correct answer. B will be the answer. Okay, the next compound question is cobalt 3 chloride forms several octahedral complexes. Cobalt 3 chloride forms octahedral complexes with ammonia. With ammonia, COCl3 gives octahedral complexes. Which of the following will not give test for chloride ions? Test for chloride ions you should not get answer means you should not have Cl minus in the structure. There should be no Cl minus in the structure. So we will see it is octahedral complex means coordination number is 6. You should have 6 ligands in the structure. Now if you write 6 ligands using 5 ammonia, here it will be CONH3 5 and 1 Cl will be inside and 2 chlorines will be outside, and this certainly will give a precipitate with silver chloride. So this can't be the answer. In this case all the 6 ammonia molecules will be acting as ligands and therefore 3 chlorides will be outside. Once again you will get silver chloride precipitate when you add silver nitrate because of the presence of free chloride ions. And coming to this one, you have 3 ammonia and 3 chloride ions. Therefore, 3 plus 3, 6 ligands will be inside the coordination sphere and the structure will be CONH3. So, only 3 ligands. So, you have to take all the 3 chlorine atoms inside and this will be the structure. Of course, in this structure, all the 3 chlorine atoms act as ligands and there are no chlorine ions outside as chloride ions outside the coordination entity, and therefore this compound certainly will not answer the test for chloride ions with the silver nitrate. And in this case if you see 4 ammonia and we need to complete 6 coordination number, 2 Cl inside and therefore 1 chloride will be outside, which will give answer to silver chloride test. So silver nitrate test. So these can't be the answers and therefore finally the answer is C, where with the coordination number 6 all the 3 ammonia and chloride molecules atoms or ligands will act as ligands and groups will act as ligands and they are inside the coordination entity where chlorine is not present as Cl minus outside the coordination sphere. In this question, among the following, which one has the highest ionic conductivity? To get highest ionic conductivity, we are supposed to have highest number of ions in the solution. And we have to see, in this case, which one will produce highest number of ions in the solution. If you go to A, 4K plus and 1 FeCN 6 4 minus. So 4 plus 1 total number of ions will be 5. And in this case you have 1 ion of the complex plus and 3 chloride minus. So the total number 1 plus 3 it will be 4. And in this case 1 ion from CuNH3 for 2 plus which is neutralized by 2 chloride, so 2 Cl minus and therefore okay, so this is 1 plus 2, it will be equal to 3 and here it is not an ionic compound, it is a neutral molecule, so N is equal to 0. So which one has the highest number of ions? It is A with 5 number of ions and therefore the answer is 5. A with the number of ions 5 will have highest ionic conductivity. Okay. The next one is The existence of two different colored complexes with the composition of CONH3,4Cl2 plus. CONH3,4Cl2 plus has two colored complex. This exists in two forms. So the same compound existing in two forms means there are two isomers with the same molecular formula. So if you go to see this is an octahedral complex with the if you see, this is the arrangement in the cis form, and the other arrangement will be like this. Trans. So these two are having different spatial arrangements, due to which some of the properties are different, and therefore this single molecular formula exists in two different colored forms. So the existence of two different colored complexes is due to the presence of cis and trans arrangements, and therefore the answer is B, geometrical isomerism. The last but one question is question number 29. The number of stereoisomers shown by COEN twice Cl2 plus. COEN twice Cl2 plus is. How many total stereoisomers means both geometrical isomers and optical isomers, both should be considered. Now to look at the geometrical isomerism, if you look at this, you have one cis form, this is cis, and the other one will be opposite arrangement of the identical ligands. This will be trans. Okay. If you consider these two, this is cis and this is trans form. So there are altogether two geometrical isomers. Now to consider the optical isomers, if you go to cis, this has, these are geometrical isomers, cis form and trans form. Next, if you go, the cis form exists in two optical forms. One is dextrorotatory, and its mirror image, which is non-superimposable, is a levorotatory compound. So it is not 2 plus 2. Cis itself is one of the isomers here. So 2 here and 1 here, and therefore you have altogether 3 stereoisomers. So the answer is cis form shows optical isomerism D and L, trans being symmetric, no optical isomerism. So total number of stereoisomers is 3 is the answer. Okay. Okay. If you go to see this, the formula of penta-aqua nitrato chromium 3 nitrate. We'll write the formula. Chromium penta-aqua. So it is water 5. Penta-aqua. Nitrato means NO3. Chromium nitrate. Once again it is nitrate. Okay. So nitrato. Nitrito is NO2. This is nitrato is NO3. Now in this formula we have to select the correct one. Here if you see, chromium is 3 plus. So if this is 3 plus, this is minus 1, nitrate is minus 1. So it will be plus 2. And this is minus 1. So how do you balance? So this should be 2. So nitrate 2. So where is the correct formula? CrH2O5, NO3, NO3 twice, and C should be the correct answer. So, this is the correct formula of penta-aqua-nitrato-chromium 3 nitrate. Okay students, I have discussed only some of the questions in this session. There are many questions and this lesson has no numericals. If you keep studying this again and again, if you go through this lesson, if you make sure about the concepts, if you understand the concepts and study again and again and fix these concepts in your mind, answering the questions from this lesson will be very easy. So I advise you all not to leave this lesson, go through the topics of this lesson again and again, revise, and you will find answering not only your annual examination, even CET and NEET questions you can answer very easily. Okay students, all the best.